Всем привет! Я Артем Шишкин. Доклад у меня про небезопасные конфигурации таблиц страниц. И прежде чем я вообще что-нибудь начну рассказывать сегодня, обязательная часть любого выступления, когда вы работаете.
Welcome everyone. I would like to introduce myself, and I have to put up disclaimer. It's a mandatory part if you're working for a big corporation. All I'm going to speak about today, it's my opinion. Not necessarily it reflects the opinion of my employer, which is Intel Corporation. I just wanted to say this before I begin my presentation. I'm working as a security researcher in Intel Corporation, in the Intel Storm team. Strategic Offensive Research and Mitigations is the name of the team. And today I am planning not to really translate or transliterate terminology, because I believe you know these terms very well. I'll be using native English terms because it's much easier, especially we have a very professional and very knowledgeable public here. So, strategic offensive research and mitigation. I will not be translating these words. And on top of that, I love Windows. That's it. All this kernel enthusiast and Windows bug, I've been involved in that for many years, and that's my scope of research and interest, and you could say a hobby on top of what I'm doing professionally at my workplace. And I wanted to speak today about virtual memory, because the page tables, they are the mechanisms of bio settings, let's put it this way. But I understand that not everyone has to deal with this phenomenon. So, in the very beginning, I guess the first part of my presentation will be very boring about this virtual memory, Intel x86, because it seems like this is the predominant device on the market. The concept of virtual memory is the following. We have a physical memory, these DRAMs, which are being installed into the motherboard, and the CPU, the processor, could have been working directly with this memory. Could have. But there are certain nuances when you want to build a more scalable system, and the safer one for that matter. A little bit later I will touch upon that in greater detail, but the main idea is that here we have some memory address space, which is actually the DRAM planks, and we have the virtual address space. And there are certain rules of translator or morphing of these physical addresses into the virtual ones. And here I'm showing just that on my picture. This is the virtual address space, which has been translated into physical address space. How does it happen if we dig down? Memory is being split into certain basic units. The adopted terminology is the page of a memory. As a rule, at many architectures, not at all, but at many, the size of the memory page would be 4 kilobytes. And again, when we will be looking into the composition of the pictures, even mathematically it will be making sense of why such a basic unit has been chosen. But nevertheless, our memory is chunked, so you have the virtual page, which has been projected into a physical page. And how could we build such the virtual physical space? Simply, you go linear to map everything and project everything in linear manner. But I'll be using the word mapping. And it all would be good. But speaking of memory, we do not always have a lot of it. But the processes which are memory intensive are many. So what can be done? We can project memory in parts, by segments. Here on the picture it makes sense that here we have some loopholes with empty space. And every time when if you're programming something not very correctly and you have an error, access violation, very often you are simply using a certain indication which is not projected into anything. So we have a page fault, which in turn is translated into operation system as a process violation. And among other things, we do not have to project the page in the ratio 1:1. Not each virtual page, with its physical number, so to speak, would be equal to a virtual page number 1. If it's a physical number 1, it is not necessarily virtual number 1. 2 does not equal 2, and so on. First of all, we may be having some holes, which is not a mapped page. And secondly, we may map these pages without any order, like I've tried to show it with this arrows, like a virtual page could be laid in one sequence and order, the physical ones go in different order and sequence, and the virtual pages may be also referring to the same physical memory. And then what do we have? It looks like we have some regions of contiguous memory, while some other regions have it all over, mixed together, and yet other regions where the memory would be shared. It's like a common memory. And what is the common effect or common result for different virtual addresses? We will be referring to the same physical page, and it looks like it's a shared mapping, just a general projection. Well, shared mapping, as I said. And what are the benefits of this situation? Why do we need all of that? First of all, I have to mention that a virtual memory is installed at most of the modern platforms. If we miss all the micro type of controllers, where the memory could be 2 bytes, basically, we do not need it because we're working with just one firmware. But the bigger system, all bigger system, they are using virtual memory because the concept is quite old, but it's still very, very good. Why? Because first of all, we can virtualize memory as a resource. Our resource are that whole set of memory in these DRAMs installed on the motherboard. But nevertheless, we can create a visibility for the executable applications. I mean the visibility that we have a lot of memory. Simply, some memory has not been projected, other memory had been uploaded to the disk and then reloaded back. But the execution environment believes that it has all the memory accessible to it. And this is much more comfortable in execution. In addition to that, this mechanism enables us to isolate the environments of execution from one another, even in one operational system. I'll be speaking about Windows, because I'm confident. Yes, I know that in Linux it's the same, but I will be referring only to Windows. If there is a process, this process has one virtual address space. If we're launching a different process, even if we launch 2 similar processes, like 2 calculators, for example, their addresses may be the same, but they are referring to different physical memory if we're speaking about the data usage. How come? It happens simply because for each process we are doing their respective tables, which project physical and virtual pages in a different way. So we have an isolation situation. In one process, there will not be page tables which would be describing the memory of different process. Next is the question of efficiency, and it is tempered by the memory fragmentation because some regions have been reserved and we may have the smaller fragments, and these smaller fragments which are disintegrated, we can project them into some contiguous region of a virtual memory, which is also very convenient. What else enables us to make this mechanism operational? It enables us to do very precise tuning of the protection attributes for each piece, for each segment. We can do very precise protection settings and many other benefits. And perks. And the whole idea is that it's cool. It's supposed to be cool. So the idea is clear, and now I will be speaking about implementation, because it's all about implementation of any mechanism. And I'll be speaking about x86 long mode paging, but I will not be speaking about this classic protected model where there are only two levels of pages, because we live in the year 2019. And right away I'll be speaking about x64 and about long mode paging. The only difference is the number of the page tables, the level of the page tables. Long mode paging is implemented as the four-tier page table. The indication is on the 64-bit platform, is 64-bit long, but only 48-bit are being used efficiently, because the central addresses are limited by the 48 bits, not by 64. And now you'll understand why. But I absolutely have to mention that there are also the five-level or five-tier page tables, because they're very interesting projects. And it means a lot of memory. And speaking about the 4 levels, it's very hard to stay on the 4 levels only. I'm not confident. And by the way, these are server platforms, and I'm not fully confident starting with which generation 5-level support had been implemented, but the idea is that these virtual addresses are being expanded to 64-bit. Within one processor, we can address much more memory. The root of this page table fits in the CR3, its architectural registry, and all the addresses are of course physical ones. And CR3 registry has this physical address. It's a base of the page tables, which will be used by the processor when it will be fetching something from the memory. And on top of that, the page tables can project chunks, not 4 kilobytes each, but there's also such a mechanism as a large page, huge page, and when the page will be 2 megabyte and 1 gigabyte. Right away. And you get the gigabyte from each page, and that's cool. And if we understand this slide, it's all very easy. And this is the example of how it is all working. First of all, I will make this claim. In the 64-bit regime where the paging is on, processor is always operating only virtual addresses. So when the fetch is happening deeper on the level of hardware, then memory management unit is activated. It does everything that you can see on the picture right now. Namely, we have a virtual address on the right in the top. It's 0xFF03, all of that. So a little bit lower, where you have the line with zeros and ones, it's the same number, but in digital code. And in the binary code, because we divide 12, 9, 9, 9, 9, 9. Simply 16 segments would not be convenient on the picture, so that's why I've made it binary. So this virtual address translates into these 16 bits, zeros and ones, and they're being grouped. The smaller part will be 12-bit, everything else is 999, and then 16-bit, as you can see on the left, which basically does not even participates in the process of the page walk. That is. Okay, now it's becoming complex. In the process of transformation. And speaking about the CR3 registry, I've mentioned about this in the previous slides, the root of the page table, it points to a physical memory. What is in this physical memory? Basically, this page table, consisting of the logs in this page table. It's a page table entry, which we have here. And what's going on next? We can take a smaller part, or younger part. PML4 table index on the left. It's an index of the PML4 table. It's the very table to which CR3 register is pointed to. And this is the number 9-bit. If in the 16-bit you render it, it will be 1F0. And this 1F0 is basically the index of this table. So we find page table entry with index 1.0, and it contains the address of the next table, which is a PDP table. And this process repeats itself 4 times in a row. Every time we calculate index out of the virtual address, we figure out the index, then we take it about the page table, then we go PML4, PDP, page directory, and number for page table index, and finally we go to the list of physical addresses. This will be our final physical address, to which memory unit will be calling on. So the virtual address is this, and the physical address is what we've taken from the last page table line. And like I said before, here we have a chunk of 4 kilobytes each. And I'm hoping that this part makes sense. On a separate note, I would like to say about the older part, which is a 16-bit. It says that this is a canonical part. And before that, I was also saying that virtual addresses are limited by the 48 bits. Because we have the 4 levels of pages, each one is 9-bit plus 12 for this shift into 4 kilobytes, chunks of 4 kilobytes each. And what do we mean by canonical part? It means that simply we've agreed about the following. All bits in this part, in this 16-bit part, have to be either zeros or ones. And if we will take a look at next will be the picture. I will actually show it to you in a graphical way. But for the time being, I've mentioned about that you have to have either ones or zeros in this part. If there will be anything else, then we will have the general protection fault. Since it would not be a canonical part, if the CPU will call to a virtual address which will not be a canonical address, we'll have an exception. Not even a page fault, but a general protection fault. That is, it's a different type of exclusion. And here, it's all the same. Simply how the circuit is working with the big pages, not 4 kilobytes each, but let's say 4 megabytes each. Let's compare it with the previous slide. You know, I'm alterating, and you can see it immediately. Simply one level of page tables is falling out, and 21-bit is used for this shift within the chunk of 2 megabytes each. The rest is the same. And basically, it depends on how you will set up the page table entry of the previous page table. But I can touch upon that a bit later when I'll be speaking more about the format. Again, the same happens when we are using 1 gigabyte pages. It's yet another layer of pages simply is falling out. We have a 30-bit offset within a page size of 1 gigabyte each. Why do we need different sizes of pages? First of all, if we, or let's say, if we have 64 gigabytes of memory to build the page tables of 4 kilobyte chunks each, it will take a lot of memory because it will mean a big memory consumption. And yes, basically it's like the saving factor. And now, just off the top of my head, 2 megabyte page, large page, are using Windows kernel. Not only kernel, Windows has a capability to use the continuing physical pages like 2 megabytes each. But the gigabyte pages, what comes to my mind is UEFI firmware, because when it starts, it immediately takes away all the memory that it can find, so that to be able to describe it very fast, it's all protected by pages, by 1 gig pages, and it's very compact. It does not take a lot of space, and everybody's happy. Well, now page table entries. The format of these entries is about the same. And I said it's about the same, but it's not like sometimes the difference is 1 bit. But the format, very, very soon I will show it to you. It points to the next page table or to a final physical page, depending on a level of a current page table. And here we have something special. We have bits in this thing which are distributed across all the subsequent pages or tables. For example, if we have a bit RW for reading or writing, for example, if we just said just read on a higher level pages, then let's go back to our picture. For example, if somewhere at the PM4 for this entry we said, okay, it's only for in the reading mode, then all other tables, doesn't matter what they contain, they'll be on the read mode. Or a user supervisor in a bit is different from the kernel mode. It's the same. The stronger security attribute suppresses all the lower page tables. And if we said that, okay, it's a supervisor page for a 1 gigabyte region, whatever the lower pages are indicating to, it will be no, it's vice versa. Not the supervisor, but the user, because supervisor has more privileges and user has less privileges. So if we already set less privileges for the higher page tables, all others will be, of course, with the lower privileges. And lower privileges will be assigned to them. Simply for the sake of example, bit XT and security disable. This is very important, and it will be good when you and I will be doing the scanning of these page tables. So the format, there are a lot of different fields, and the lower 12-bit, the junior 12-bit is where you have the P, RW, ES, these type of bits. And since we are using the shift within the chunk, we have the junior 12-bit sort of free, and in these bits you can put something of the service nature, and I will mention about it later. Then PTE contains the address of the page table or address of actually a physical page frame. And then ignored part, reserved part, protection key, which today basically plays no role. In my presentation, I mean, it plays no role. And is execute or disable. This is my implementation on the examples of 80X. And now, important bits. First of all, it's present, whether anything is mapped or not. Next, those bits responsible for protection. Read-write. Can you simply read in this region or write user supervisor mode? Can this region be given access in different modes? I'm saying that this is a user regime and the kernel regime, but actually we have the protection circles, and I'm just skipping that, but actually, if we take into account these protection circles, then for the 0, 1, 2, it will be a supervisor, but for the number 3 circle, it will be a user mode, respectively. And execute disable bit, which tells us that whether you have to execute code from this region or whether you should not do it. and another part of bits are responsible for caching, because we can ensure different access to a physical memory. You can switch on your caches or switch them off, or you can just do the projection. It's like a communication with hardware. This type of transactions are usually not cached. There are also different types of caches like write bind, write back, all these things. But again, here they do not have the same significance within my presentation. And so I probably could mention the global bit responsible for dumping like cache if you're switching from one page to another, because there are common pages which are always projected. They're always projected to the same physical memory. So when you're switching between the processes and these pages, if they're marked as global, then why would you flash them from cache? One important detail about reserved or ignored fields. Ignore the fields which you should not touch. Let it stay the way it is. What do you say now? Ignored or reserved? Reserved. No, reserved should not be reserved should not be touched, but ignored, more interesting. Ignored field means that basically hardware could not care less what's in there. So we can modify it any way we want. It will not have any effect at all. And due to this thing, we have the bigger space for experiments in memory management for operational system, because when a page is not mapped, if you look at the picture, PTE not present, the very first bit present is 0. If it is 0, all other bits respectively being ignored. So the memory manager can write any ancillary information into that. So if this page is uploaded onto the disk, then if we simplify it, we can write address on the disk from which you have to download this page into the memory if the application will try to address it. And another example, Windows in the senior part, ignored, is using the already projected PTEs. This is the picture on the top. And if you can see on the left, there is a little ignored piece. It's a small present for the memory manager, which can store hashes into it. So it will be more convenient and faster to calculate which page belongs to which process. These kind of miracles are available in the system. And now, finally, here we go. It's the main topic of my presentation. The whole idea of the presentation is when we are facing the phenomenon of a virtual address space, we want to scan page tables and to find something in them, whatever is misconfigured. And to this end, we need to scan them first. To scan them, first we were writing it manually on, just on the pictures, but as a matter of fact, it's an algorithm of bypassing a tree. And when we have an operational system and the memory management or memory manager is operational, my personal suggestion is to pay attention only to the hardware component. We have to pay attention to whether the page is projected or not, because the memory manager is introducing its own semantics into the logs of the page tables. We can ignore it if we're looking for any errors, because if the bit present is there and the hardware is operational, there is nothing you can do with it. No logics of memory manager will affect it. If in the page table there is a present, mark or tick, the mapping is there. Why am I speaking about that? Because if we are focusing on the logics of memory management, depending on how we are going to scan the page tables. In particular, if we are going to scan them from WinDBat, and the kernel is still operational, and it's introducing changes into the projection on the go. So whatever you scan in WinDebug, it will not necessarily will be reflecting the correct reflection of reality. That would be great to take it in ITP and the scan, but it's a different story. Or we can use the hypervisor also, and the results will be even more precise. It's a little food for thought. Another part, which may seem to be very obvious, but for some reason we do not stick by it. It's parsing page table entry. These very pictures you've seen on the previous slide with different bits. And to do the correct parsing of them. Because, for example, you have the bit page size. Okay, let's go back a little. Page size. It's 4 kilobyte PT. Oh, I'm using the same picture everywhere, so I do not have it. Okay, there is a page size bit located somewhere at the ignore part on the right after PTG global. And if PTE within the page table is of a higher level, it will mean that we point, whether we point to the next page table or we are referring to a memory. So in this way, we're saying, is it going to be a large page or the next page table? And therefore, when we do the scanning and this kind of bits, we have to pay attention to them. Because physical address of a page, yes, we've taken it, but it's not a given that you have to continue, try to parse it into the next page table. Maybe it's a final address. And then, for the final address, you have to look for your protection attributes.
And correspondingly, it may sound silly, but you always have to check whether the page has been projected or mapped or not, because otherwise we can't be sure about the results. So, this is our approach to the static analysis of configuration. So this is the picture that I wanted to mention. The typical layout for an operating system. The lower part is user mode addresses, where applications live. The older part, the higher part, kernel mode, privilege. So user mode regions are many because we have many processes, and the kernel is one, and it's not always mapped, depending on whether KPTI on or off, but the kernel is just one for everyone. And in the middle, we have a non-canonical address region. The addresses where in the upper 16 bits there are other things as zeros or ones. So we can't physically access those addresses. So let's go on. What are we going to check against? First, the bit user supervisor, the ones responsible for checking whether the table is available in user mode or in kernel mode. So it looks like a naive idea, but all kind of things happened, and quite recently, maybe about a year ago, when the API patch for Windows was launched, for instance, for Windows 7. So for some strange reasons, we got a whole region open up, and not just a region, but a PML4 page table region. So it appears that we can build any page tables from user mode. So, and basically we can read, write, do everything with any physical memory, because we control the high-level page table. So who knows then? You also have to understand one other thing. Page tables can exist in different devices. For instance, in some hardware, memory management unit can also exist. And just for the curiosity's sake, scan it and see what kind of configurations you'll find there. As a developer, I can tell you that you're usually too lazy to try and play with these things, and you can do something quick and dirty, and a lot of people do that. But you may not even be caught doing that. But on the other hand, even such basic things are good to check. There's a principle in security or not in security, how best to say, where something must be either writable or executable. When these things come together, it doesn't look great because you can't know what people can do with that, because that could lead to code execution. So therefore, it's not a bad idea to check, just in case, if the table is writable and executable at the same time. This approach, actually, this idea, actually, did a good job for me to do the latest kernel exploit. Actually, this was the reason I was scanning all these pages. Talking to Microsoft, they said everything's okay, I can share it, it's all by design. So whether it's like it's good or bad, but such things exist. Microsoft knows about that. So I looked and I found that there are regions in the kernel that are mapped for execution and writing at the same time. So you can actually abuse them because of that. In particular, the UEFI region is fully mapped as both executable and writable. Also part of the kernel itself, and quite a big part, 2 megabytes large. And cache manager functions are sitting there, so you write it immediately and you can execute it. Then drivers, or legacy drivers, love doing all sorts of allocations when they're both executable and writable. And there are APIs. An API, which is called maplow space, which is used to map a physical address to a virtual address. And I'll speak about that in more detail in the next slide. So all these finds can be only abused if Hyper-V is enabled with security mode disabled. So because Microsoft did a good job, they implemented security at the hypervisor level. When you're using a hypervisor, we have extended page tables, and right there, they're keeping an eye on the page table configuration. I tried it myself. I tried writing in some parts, and it didn't work. I tried to execute other parts, and I would just stall at the same place, just getting a fault. So when VBS is on, so abusing regions doesn't work, and it's good. Microsoft are great guys. Now about UEFI range. Modern firmware allows services for the operating systems, in particular runtime services. They are used so that as UEFI variables could be changed, even if you want to call a reset. The operating system uses runtime services. So, and here what you get, we get a semantic gap. I'll use the English term, semantic gap, because the firmware doesn't assign security attributes as a rule. It maps everything as RWX, and that's it, nothing less. So that hoping that the operating system will cope. But how can the operating system cope? It doesn't have additional information to map this region, so it maps it just like the firmware indicated. And this is why we have it stays in a runtime in the runtime with the same attributes as RWX, so they can be rewritten or And they can be, all the function point table is a health runtime services block, and they can be triggered by reading a UEFI variable, for example. And again, this thing is blocked by virtualization-based security. Everything I mentioned about the previous slides works here as well. So Microsoft are great guys. Now about this semantic gap. Sorry, I forgot the Russian word. So there are two functions. One is a legacy function, maplo space, and then there's maplo space x. It's an extended version that's been introduced in almost the latest version of Windows. If you take a look at the prototypes, you see that there's a difference in just one parameter. In the past, it would accept a type of caching as input, and now it accepts type protection type. And how is it all done in Windows 10? Maplo space calls an extended version inside. So therefore, the caching parameter implicitly turns into a protection parameter. And so we only got three types of caching that we can use. Firstly, non-cached, and it's converted to page no cache, a page read write execute. So we got RWX. With the cached ones, same thing, RWX, and only write combined ends up being unexecutable. So we got the situation we get is like this: drivers can abuse it, and not only to map some MMIO, not only hardware resources. And it turns out that drivers like the legacy feature because it supported null versions. And as a result, it turns out that implicitly we map all these regions as RWX. So this is the bad thing. Also, we can map not only DRAM, not only the physical memory, but we can also map memory, map I/O, all regions that are also reflected in the physical address space, but hardware resources are mapped there. So this is the way for the CPU to program the hardware. So different things happen, and it wouldn't be a bad idea as well to check where we map the page table, because if we map the user mode to some page that ends up in an MIO device, and in particular if it maps to the DMA engine, then you consider things done. We'll be able to rewrite random physical address, which is not at all good. And in particular, it happens quite a lot with hypervisors. There the page table is EPT, but the S is like this. When the hardware exposes directly to the guest, to a guest virtual machine, the real hardware. So we start reprogramming the DMA engine and start writing memory everywhere, and that's host memory, the hypervisor memory. So this link is actually exactly about this. Also, we have such a phenomenon where the mappings are shared. They can be shared by different modes, user mode and kernel mode, and therefore it's not a bad idea to check if a lower privilege mapping has access to some other things. For instance, if we can change the kernel mode, of course, you can do it safely, but this should be considered as a bell saying that you need to take a closer look. Well, scanning can be automated, and please look at this more carefully. Or for instance, we have some kernel mode mapping, and you can use some sensitive, you can read some sensitive data from the user mode. And there's also a great example in Windows. It's by design. There's a region called shared using data. It's one page that sits in the kernel mode, but maps to every process. So how does it work? In kernel mode, you can read and write, and in the user mode, you can only read. Everything is done safely. More than that, there are no pointers there, stored there, no sensitive information either. So everything is done safely and securely. But you have to pay attention to this example, because if you do scan and if you haven't found a single mapping between user mode and kernel mode, you have to think twice. Maybe something's wrong, because this page should be there. So, so much about static scanning. And there are also problems that come up only in dynamic modes related to caching. So there's this subject. When attributes of page tables, and not only attributes, but also the address, are cached, so that the CPU shouldn't need to to carry addresses over these, so they just pick it up from the cache. Also, there are caches that keep parts of page tables caches. So they cache all the list information, PFN, which is a physical address, RW bit, it's a read-write bit, an executable bit, US bit, XD bit, protection keys, dirty flag, memory type. So these caches exist per CPU. So for each thread, there's a separate cache. And because this is a shared resource, because the page table is a shared resource, and caches are separate everywhere, so when we change something in the shared resource, it wouldn't be a bad idea to inform other cores that the mapping has changed. As a rule, the operating system sends an IPI as inter-process interrupt, and makes all kernels, whatever they would be doing now, all cores, I'm sorry, to process this interrupt and to update the mapping, so to reset the caches or flush the caches, and next time so that new information should be loaded. Correspondingly, because the operating system is providing an API to change mapping attributes, well, same thing as the virtual protect function or feature that replaces Rx by RWX, RW, so we can call these functions right from there. So therefore, there does exist an attack surface from user mode. So this part should also be checked to the effect of how well the cache synchronization is implemented between these processes. Because situations may arise where we can find ourselves in a race condition. We'll be flushing something, and then something will not be flushed to the end, and the process will be still using an old physical page, while its virtual address has already been mapped to another physical page. And then it will turn out that the memory manager will put the physical page into a queue for use, so it will be allocating it to somebody else, whereas some other process in some other CPU core will not have update information and will keep using the old physical page. And going on, everything will depend on where this physical page will be reused. For instance, it can be reused by some privileged component, a component of the operating system, and then it'll end up in the old page cached from user mode, offering access to the component that is not supposed to be accessed. And so this CVE is an example of that. So these things are more difficult to detect because you need to do reverse engineering, source code reading. But the bugs that result from this approach are actually quite good. Guys from Google Project Zeros showed us in a real example how this kind of vulnerability can be exploited. Okay, great. So basically, this slide includes all the references that I mentioned in my presentation, and guys from Google Project Zero are here. Total meltdown. It's about the case where the PML table 4 was open. So this slide is available, and you can just spend some time reading. Especially, please use the first link. It's the most required link in your life. You don't need to read any books. So there's Intel Software Developers Manual, and it has everything with pages, with illustrations. And so what's important, everything there is truth compared to other books. Recommending to everyone. Only 4,000 pages, but they're worth it. So thank you.